So what's up guys, it's me again, the Round Bottom Flask, and welcome to the video lecture series for the electronic structure of atoms. This is the last part of our video lecture series for electronic structure of the atoms, and in this video I will discuss electron configuration. So again, electron configuration describes how electrons are distributed in the orbitals of the atom. Now, let me draw your attention here in this part. So this is the electron configuration of the representative atoms, and that is also indicated in the periodic table. Now, in the electron configuration, so this number here indicates the energy level or the principal quantum number of that orbital. Of that electron, and this one indicates the type of indicates the shape or type of the orbital. So may it be an S, P, D, or F. While the subscript after that letter is the number of electrons residing on that kind of orbital. So let's say in lithium, its electron configuration is 1s2 to s1. So that means in 1s2 to s1, 2 electrons reside in the 1s orbital and 1 electron resides in its 2s orbital. For let's go further down. Let's say for carbon, 2 of its electrons are in the 1s orbital. 2 of its electrons are in its 2s orbital, and 2 of its electrons are in the 2p orbitals. Okay, now this electron configuration that I have shown here, and also that the one also visible in the periodic table, is what we call as the ground state configuration. So when we say the ground state, the electrons are in their lowest possible energy states. That means they occupy the lowest possible, the orbitals of lowest energy that they can occupy. So they can be a more detailed representation of the distribution of electrons in atoms is orbital diagrams. Now, in orbital diagrams, it shows a complete picture of all the quantum numbers of all of the electrons of the atom, because this is our orbital diagram here. If you notice, it shows the electrons, it shows both the principal, the quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. So here, one major difference of orbital diagrams is that it shows the spin, with respect to the regular electron configuration, rather, is that it shows the spin quantum numbers of the electrons, which is denoted by our half-headed arrows here, which is in the boxes indicating representing one orbital. Now, the half-headed arrow pointing upward indicates that the spin quantum number of that electron is positive 1/2. If it's pointing downward, that means its spin quantum number is negative 1/2 by convention. So there are several rules that we need to follow when we're writing electron configuration. The first one will be the Aufbau principle, wherein when we fill up the electrons, we start at the lowest subshell or the lowest energy level. So the first one that will be occupied is the one with the lowest value of N and L first. So obviously, in every element, the first one that will be occupied is the first energy level, and the orbital with the lowest value of L at the first energy level, since L can have values from 0 to N minus 1. L can have values from 0 to N minus 1, and since our principal quantum number, or n, is 1, it can only have one value, which is L is equals to 0. And that is our s orbital. So the first thing that will be occupied in the first orbital that will be occupied when we're writing the electron configuration according to Aufbau principle will be the 1s. Okay? So if we have the same values of n in most cases, the s orbital will be filled first, followed by the p, followed by the d, followed by the f. This is because among the orbitals, s has the lowest energy, and f will have the highest energy. Next is Pollys exclusion principle, which indicates that no two electrons should have the same set of quantum numbers. So let's have an example wherein we apply both the Aufbau principle and the Pollys exclusion principle. So we have here lithium with an electron configuration of 1s2 to s1. We try to draw its orbital diagram. So when we draw orbital diagrams, we first place blanks and under those blanks we indicate what is the orbital that's representing that blank. So here we have 1s and 2s. So since 1s has a lower principal quantum number than 2s, it is the one that is filled first. So we place that one here. Now remember that orbitals can accommodate at maximum 2 electrons. So since 1s orbital only has 1 electron, we still have one more. The next electron will be here in order to completely fill the 1s orbital. Now the next electron that will be paired to this lone electron here will have the same values of n, l, and ml. Okay, so in accordance to Pollys exclusion principle, hindi na pwede na parehas sila ng spin quantum number. So how do we do that? So we draw another electron. We place another electron here, but this time it is pointing downward so that it will not have the same quantum number as the electron as this electron here. Next, we go to the 2s, following Aufbau's principle, to fill up to place the last remaining electron. Lastly, we have the Hund's rule, or Hund's rule rather, of maximum multiplicity, which states that when you're trying to distribute electrons in an atom with more than one orbital, you have to make sure that the distribution of the electrons such that it will give you the maximum number of spins, the maximum total spin possible, or what we call or the more technical term here, that it will give you the maximum multiplicity. So multiplicity, this is the formula for multiplicity, wherein S is the sum of the spin quantum numbers of all the electrons in an atom. So this Hund's rule of maximum multiplicity is applicable to what we call as degenerate orbitals, or orbitals that have the same energy. So let's have this one here. So let's have the electron configuration of carbon at the same time. It's what they call this? It's orbital diagram. So if you notice, the two 2p orbitals here are the two 2p electrons here are in two different 2p orbitals, not that this one is on the same orbital as this one. That is because that when you pick that because when these two electrons are in the same orbital, one of them will have a spin quantum number of -1/2, and that will result with a total spin of 0. However, while in this one here, in this distribution of electrons, the total spin for this one is 1, because this is +1/2, this is also +1/2. Since this is +1/2 and -1/2, they will cancel each other out, so this will be 0, this will be 0. So the total spin will be 1, and thus the next electron is placed there to maximize the number of spins. Now, how do we draw the electron configuration of an elemental ion? So let's have an example here. A fluoride anion. So we add or we remove electrons depending on the charge of our elemental ion. So let's have, for example, fluorine to fluoride anion. So fluorine has this electron configuration. If this is converted to a fluoride anion, it will because of its charge na -1, we'll need to add one more one more electron. Okay, and so where will the electron be added? It will be added on the outermost shell. The outermost shell is what we call as the valence shell. So since the outermost shell, or the outermost orbitals of your fluorine is 2p, so therefore when it becomes fluoride, we add here to this 2p orbital wherein there is an unpaired electron there. So the resulting orbital diagram and electron configuration, so from 1s2 to s2 2p5 of fluorine, it will become 1s2 to s2 2p6 of fluoride anion with this electron configuration. When we go down the periodic table, or rather when we write the electron configuration of elements in the period 3 downwards, their complete electron configuration becomes more longer and becomes more cumbersome to write. So one way of I don't know if this is correct term, expediting this is by writing its condensed chemical formula, or condensed electron configuration rather. So let's have silicon here. Now silicon has this electron configuration. Okay. Now if you notice, this one here, this part here is also the electron configuration of neon. Now if we go back, if you look at our trusty periodic table, silicon here precedes neon. Okay, so when we write our condensed electron configuration, this inner configuration of this electron configuration of the noble gas preceding this element will be written as a symbol. Shown in brackets. Okay, so we try to condense this one here to this one here. Okay, and this one, which is not included to the noble gas configuration, is what we call as the valence orbitals. Now the valence shell that I am talking earlier is actually the energy level, or the n of that valence orbital. So elements in the periodic table can be classified or can be grouped according to their valence orbitals of shells. This is important because their chemistry and their properties are actually because of their valence orbitals. So let's have this one here. So groups 1a and 2a belong to the s block, and groups 3 to 8a, with the exemption of helium, belongs to the p block, because obviously their valence orbitals are s and p orbitals respectively. The transition metals, this group here, are also known as the d block elements, because again their valence orbitals are d orbitals, and the lanthanide and actinide series are also called f block elements, because their valence orbitals are f orbitals. So in this image here, this is a guide on how to write your electron configuration. So if you notice, this one looks good here. It follows the Aufbau principle from here. Then instead of going to the 3D, from 3p, instead of going to the 3D in accordance to Aufbau principle, it actually goes to the 4s, then to the 3D, then diretso siya ng 4p, and so on and so forth. That is a phenomenon observed by period 3 elements going downward. So in the D block elements, so the valence shell, ideally, it should be written in this manner, based on our comprehensive guide. However, there are some cases that it could be written like this. Well, both are correct, but the more preferable configuration will be this one here. Well, in some cases, for example, in iron, so iron will have a electron configuration of this one. Okay, this is more correct instead of this one because there are some transition metals or some d block elements wherein, even though the d subshell has not yet been filled, it will fill the ns orbital first. Okay, this phenomenon is also observed in the f block elements, and in the s and the period 4 and above s and p block elements. So I hope you learned something from this video. I hope you find this video educational. So, and if you do, don't forget to subscribe to my YouTube channel for more videos. Once again, this is the round bottom flask. See you guys